Welcome back, and thanks for joining us again for our work through the Queensland physics syllabus. We're looking at relativity in Unit 4. This is following the textbook by Walding, which is a pretty good reference for us. And this particular chapter is about relative motion. I just want to talk about the image I've got on the screen there at the moment, the one about these little light cones and so on. It's a little bit weird to work out what's actually going on here. What we have is time in this axis that runs through the middle here. And from that, think of that as the point that you're at. And it's like you start here in the past through to the present, which is this plane here, and the future is somewhere out here. And that's why we sort of refer to the past light cone on the bottom and the future light cone on the top. Now, consider that you can move through this plane. So it's almost like if you're here in the middle, you can decide to move that way, but it takes time to do that. And as you move, time is passing. So the net result of all of this is it's like you travel along this path here to move across. Let's think about an example in the past. Let's assume you're here at one point in time, and that's the past from now. And then over to the side here, there's an event that occurs. Now, for example, it might be a flash of light or a sound waves being given off in all directions from that point, and it will spread out from that point. So what you can see happening is that sound has eventually got to reach you over here. But as that's happening, time is passing. And so by the time it reaches you, it's almost like it's gone along this path here to reach you at this point here. And then likewise, that will keep going off into the future light cone as that sound or that light radiates out. So think of that as past versus present. We are at this point here in the middle right now. Things have happened in the past, things will happen in the future, and those things will take time to reach us. And that's the concept of relativity that we'll talk about, and the concept of simultaneity that we'll discuss next section. Okay, last time I left you, I suggested you watch this video before you get to today's stuff. It's not a very long one. It's only 2.5 minutes. I hope you had a crack at that one. All right, a little bit about the past, a little bit of history. A long time ago, the late 1600s, a Danish astronomer was studying the orbits of the moons of Jupiter. So yes, we're talking about another dead white guy. Now, what he noticed was something a bit weird. If you consider on our little diagram at the top here, the sun's in the middle there, there's the Earth, and there's Jupiter out there. And what we have is this distance here between the radius of Earth and the radius of Jupiter. Now, what we actually really need to consider though is that there is the diameter here of Earth's orbit and this extra distance, which is the orbit to Jupiter. Now, what this astronomer was looking at was he'd watched the eclipses of the moons of Jupiter, and he noticed that when Earth and Jupiter were very, very close, like this scenario here, it was a different time to when Earth and Jupiter were on opposite sides of the Sun. And the net difference in those distances is the radius of Earth's orbit. So what he worked out was the variation in timing was a bit over 16.5 minutes at different times throughout the year. And so what he realized was this was the time it took the light to travel across that extra distance of the radius of Earth's orbit. So when we're close to each other, there's that small distance the light's got to travel, but when we're on opposite sides of the sun, it's a far bigger distance, and the difference is this radius of Earth's orbit. And he worked out if that was a difference of 16 minutes, then that was the time it took light to travel that distance. So if you know the radius of its Earth, hence you can calculate the speed of light. Now back in his day, we didn't really know much about the radius of Earth's orbit, didn't know it that accurately, but his method for calculating is accurate to within 0.5%. So that's pretty good reasoning. All right, so today, what are our actual learning intentions? We're going to look at how motion is relative, which we sort of started discussing last time, and we'll look at how the speed of light is constant, and we'll come across this idea of simultaneity. You can pronounce it simultaneity or simultaneity, it's up to you. What we'll be doing by the end of this, describe the motion relative to the speed of light of objects. So let's think about frame of references that we started talking about last time. So we have our central idea in the middle there, which is motion. Let's look at the left-hand side and look at the classical Newtonian physics. Usually, we don't really have to consider much about frames of reference because there usually is only one frame of reference, and that's usually the Earth. As in, objects are moving here on Earth, so we pretty much say it's happening with respect to Earth. Now, on the right-hand side, we have the Einsteinian view, which is this relativity, where Einstein realized that you can have multiple frames of reference. IRF is inertial reference frame. And each of these frames is equally valid. They're all as valid to each other. Think of the idea of you're sitting on a train and someone standing on a station. The multiple reference frames are you sitting on the stationary on the train and the station moves past you, or the person standing stationary at the station, standing still at the station, and the train moves past them. And they're all equally valid. That's that idea there. Each reference frame will produce results. It will give you the same sort of results in experiments, but when we start to investigate it, we'll see some slight differences in how it actually works. The laws of physics will still be the same in each frame, but the actual outcomes that we get start to look a little bit different depending on the motion. And here's a good example of it, classic example of dropping a cannonball from the mast on the top of a ship. I don't know why you would do this, because this was sort of developed back in the days of wooden boats. And if you dropped a cannonball, well, firstly, it would be hard to lift it up to the top of the mast. And then if it did fall, it would probably fall through the deck because it was a wooden deck. That tends to be bad. But anyway, I digress. What's actually going on here? We have our cannonball here. If you're standing here on the boat, that is your frame of reference, the boat. You see the ball start at the top here, fall down, and land on the deck. And it travels this displacement, this vertical displacement here. The other frame of reference is if you're standing, for example, on the shore, watching this boat sail past, it has a forward motion. All right. So the ball still starts at the top of the mast and will still end at the bottom of the mast, but because it's traveling forward, it takes this circular path. So on the boat, you standing here on the boat, the displacement of the ball is different to if you're standing on the shore, because on the shore it appears to take this longer path in the same amount of time. If you're on the shore, it appears that the ball is actually traveling faster because it's not just a vertical component, but there's also a horizontal component, like we discussed back in Unit 3 with our projectile motion. So if we look at our summary in the green arrows at the bottom there, for both observers, the cannonball lands at the base of the mast. It starts at the top and lands at the bottom. The laws of inertia are the same in all dimensions and all reference frames. Gravity is still the same, so it's still acting on the ball, pulling it down in the same way. However, the path is different, hence the velocity appears to be different, because it's happening in what appears to be the same amount of time. The one person standing on the shore sees the cannonball travel a greater distance in that time, and we know that the velocity is the displacement over time. All right. This is bigger, this is the same. It's going to change, make it appear like it's traveling faster with a greater velocity. That brings us to Maxwell. Once again, another dead white guy who's around a while back. Basically, he did a lot of brilliant work in physics, which is obviously why we still talk about him. He confirmed the speed of electromagnetic waves, but back in his day, think of waves like sound waves or waves on the beach. The reasoning was that sound waves need air to pass through them. Sound waves won't pass through a vacuum because there's nothing to physically vibrate. Water waves on the beach need the water as a medium to move, for the energy to move through. So it was reasoned that electromagnetic waves would need their own medium to pass through. And we couldn't really detect what it was, so we called it this ether thing. We've since discovered that Maxwell was wrong on this idea, and a lot of other people in his time were wrong on that idea. Electromagnetic waves do not need a medium to pass through, hence they can travel through the vacuum of space. But the brilliant thing he's known for is uniting electricity, magnetism, and optics all together, particularly confirming that it is an electromagnetic wave. All right, little challenge down the bottom there. Pause the video, have a look at that. If you're running along and you drop a pen, where would it land? I guess the short answer to this is it's just like the cannonball example. The cannonball doesn't land behind the boat. The cannonball doesn't land in front of the boat. It keeps falling down as though that's a frame of reference. So the pen would land at your feet if you kept running. All right, so the speed of light. There's a maximum speed, which we call c. We've mentioned this a few times before. We consider light to be massless particles, and we refer to photons. They travel at this speed, 3 by 10 to the 8 meters per second. You could say it a few different ways, 300,000 kilometers a second, whatever it is, it's very fast. And that is our maximum speed limit. And the interesting thing for relativity is this point here, it's the same maximum in all reference frames at all times. And that's why we start to look at things like time dilation and so on, because it's got to change to account for this. Doesn't matter what the velocities are. Could there be faster speeds than the speed of light? The laws of physics tell us at the moment, no, that's not possible. But we'll talk about that later. Hence, Vicky Pollard, no, but yeah, but no, but yeah, but it's all a bit weird. So let's look at classical Newtonian vector addition. You've got travelling guy standing on the back of the ute here, and you've got stationary guy. The ute's travelling at 15 meters a second. Travelling guy throws a ball out at 15 meters per second. So classical Newtonian physics tells us add these two vectors together. The 15 that he throws it at plus the 15 that the ute's travelling means stationary guy sees the ball come in at 30 meters per second, which kind of makes sense. But what about as the speed of that ute increases? So if the ute's travelling at 15 meters per second and travelling guy shines a torch, the speed of the light is now 3 by 10 to the 8. So you would expect that this speed of light that the light beam of the torch is travelling at, plus the speed of the ute, add them together in this bit here, 15 meters per second plus 3 by 10 to the 8 is greater than the speed of light. But this is not possible. It doesn't happen. And this is what the problem with Newtonian physics was. And this is what set the scene for Einstein to start doing his work to work out exactly what happens at these very, very fast speeds. I'm sure most of you have been at the supermarket and seen your mum run into a friend or something when you were little, and you probably felt exactly like that scene there. So, what's going on here? Newtonian stuff is this top one. The velocity of the ball with respect to the Earth is 30 meters per second because the velocity of the ball with respect to the car is 15, and then the car to the Earth is 15, so they add together. If we think of the light beam, so think of that as the light, the velocity of the light with respect to the Earth is still going to be the speed of light. All right, and it kind of doesn't make sense because assuming your car's travelling, say, at 0.9 the speed of light plus the speed of light that the light beam comes out as, you would expect that the light beam to travel at 1.9 times the speed of light, as in the car's speed is 0.9 and the light speed is 1, so they should add up to 1.9, but this is not what actually happens. This is what actually happens down here. The speed of light is still constant, so the velocity of the speed of light with respect to Earth is still c, or the speed of light. Let's look at how that works out. Here's an example of what's going on. You can pause the video and read that little scenario there. It comes from the text, but what we've got is a couple of neutron stars. They're 1500 light years away, and at one point when these things rotate each other or orbit each other, one of them is receding away from us at 300 kilometers a second, while the other one is traveling towards us at 300 kilometers per second. But when we measure those light beams coming off them, it is still the same speed. It is still the same speed coming at us. It's not like this one here is traveling away and hence its light beam is traveling slower than the other one when they reach Earth. They still come to at the same speed. And as you see on the screen there was a Nobel Prize awarded for this work. Here's a nice little challenge for you. I encourage you to pause the video and have a look at it, read through it. Essentially what we have is rocket B traveling at 0.6 the speed of light, which releases rocket A, and he is traveling at 0.6 the speed of light with respect to B. That's what it says, velocity of A with respect to B. So the question becomes is, what is A's velocity with respect to Earth? Einstein's got a nice little equation up the top here, so you need to plug in the numbers that you know. You know that the velocity of B with respect to Earth is 0.6, so that will be the velocity of B's. You know that this guy's traveling at 0.6 with respect to him, right? But what we also know is the velocity of B with respect to A is also 0.6. Alright, so we know that this is 0.6, this is 0.6, this is 0.6. We know what C is. We're trying to find the velocity of A with respect to Earth, which is that last one that I circled. Might want to rewind the video and get that formula before I rattle over it. Put those numbers in. Okay, that brings us to the end of this one. Have a look at the check your learning. Have a look at the next section about simultaneity. There's a nice little picture on the side there for you. The reason a lot of these guys didn't actually win Nobel Prizes is because your work's got to be actually proven to win a Nobel Prize. And a lot of these guys were working in stuff that was so theoretical and so out there that it hadn't actually been proven yet. A lot of Einstein's work was proven well after he passed away. Before next time, if you've got access to the Oxford Online stuff, there's some great things in there. I suggest you have a look at this particular video on the screen, and I'll see you next time. Thanks a lot.